Okay, so continuing on. What are we looking at this slide? Acid and base strength. So HCl, is that a strong or a weak acid? Strong. How do I know it's strong? You memorized it. Let's say you forgot to memorize your acids because you just haven't done it yet and it's not the exam time. Looking at the equation, how do you know HCl is a strong acid? The key is that forward arrow. This forward arrow tells me this is a strong acid reaction. Is chloride basic?
No.
I could still say this is my acid and my base. So what would this be called? A conjugate base, but is it basic? No. So just because we call it a conjugate base doesn't mean it acts as a base. Yeah?
So why is Cl negative not basic and then forming negative?
Because HCl is a strong acid. Strong acids dissociate 100%. Why do strong acids dissociate 100%? Because the products of that dissociation are really, really stable. Meaning H3O plus hangs out and Cl minus hangs out and is not reactive. If it was reactive, it'd try to go back and make more reactants and shift the other way. HF is a weak acid because H and F minus are strongly attracted to each other. They don't want to completely dissociate. So when I make F minus, it'd kind of rather be with HF than by itself. It's not as stable, it's reactive. So if what you're making is reactive as a product, it's going to shift back as an equilibrium reaction. Hopefully that kind of explained it a little bit. Okay, base, and then what do we call H3O plus? Conjugate acid. What makes that solution acidic? H3O plus. So in a beaker, if I'm putting in HCl aqueous, again, if we had microscopic eyes, what would you see in that beaker? Water. What else? I heard a hydronium. Chloride. Anything else? No. Why is there no HCl? Completely dissociates. The reactant's not there. But then why is there water? That's a reactant.
There's an excess of water?
Yeah, there's an excess of water. Water is your solvent. So that's always there.
So does that mean that there'd be a certain concentration where there would be no water?
The question was, is there a certain concentration where there would be no water only if it's pure, and that would mean it's not aqueous. So no, there will always be water present in our reactions that are aqueous. Yes?
Does pH just go after the concentration of hydronium?
pH just goes after the concentration of hydronium. So you may have seen this in a previous chemistry class if you're working ahead. The most important pH equation to solve for it, pH equals negative log of our hydronium concentration. So if you need to get a pH, you need to find the hydronium concentration. If it's a strong acid, well, if I had 6 molar HCl, what's the molarity of chloride? 6. If I have 6 molar HCl, what's the molarity of hydronium? 6, right? It's a 1-to-1 mole ratio. So the molarity of the strong acid tells you the molarity of the hydronium because it completely dissociates. What are we looking at this next reaction? Yeah, so these are equilibrium arrows. They should look like that. And this tells you a weak acid reaction, right? So in your beaker, what is present? If you add CH3CO2H. What is that? CH3CO2H? Acetic acid. Strange way of writing it. Ic was 8. Acetate from Chem 60 we learn as
C2H3O2.
C2H3O2 minus. So what is acetic acid?
H.
H, C2H3O2 aqueous. And you can see these two chemical formulas are the same, they're just written in a different order. There's actually one other way we'll see acetic acid written.
Is it written like that in the structure of the molecule?
This is the most common because we're emphasizing, remember from the video lecture last time, COOH is our carboxylic acid group. So that's what that's emphasizing, the CO2H or the COOH. I usually write it CH3COOH, and that emphasizes that last hydrogen is bonded to oxygen. Remember from last lecture, as oxy acids, the acidic hydrogen is always bonded to an O, because that OH bond is relatively weak. Weak bond means the H plus can dissociate. So acetic acid, those are 3 different chemical formulas. I want you to recognize all of them. Acetic acid is a really common acid in chemistry and in your kitchen. Where is acetic acid in your kitchen? Vinegar. And if you took Chem 60 lab at Pierce, you had your titration lab where you do like 12 titrations, the last of which is with a diluted vinegar solution, which you determine through titration and calculation contains approximately 5% acetic acid. My point is, please memorize acetic acid, know those different chemical formulas. On an exam, you should be comfortable if I either give you the chemical formula CH3COOH or if I say acetic acid, because you'll have to go to your Ka table on the front of the exam and identify that Ka. Questions? Yes?
If we're not given the plus, how do we know that the weak acid isn't H2O? Like it's reacting as a base.
Okay, so that's the thing. So you need to memorize that. You need to be able to recognize acetic acid as an acid and not a base. And how do we know acetic acid is an acid? Because we learned to name it. So you know your oxyanion, acetate, if it gets neutralized. When I say neutralized, what does that mean to you guys? So when I say neutralize, what I'm thinking of is a charge. So my oxyanion has a negative charge. I can neutralize it with a positive charge to make a neutral molecule. The positive charge I neutralize it with is H+. So if my oxyanion is neutralized with an H+, that makes, by definition, an oxy acid. So we have to rememorize our oxyanions and recognize them the oxy acids. So again, having that list is really going to help. And I will do my best to remind you of the naming as we work through the lectures to help kind of refamiliarize yourself with these. So yeah, you have to be able to look at a reactant and know if it's an acid or a base. And that is one of the most challenging parts of the chapter. Again, which I encourage, have that piece of paper, list of acids, lists of bases, and you'll see there's not that many of them. And if you stare at them every day, you're going to remember them. Really good question. Yeah?
So if we make that list, if it's not a strong acid, then put it on the list. If it's not a strong base, then put it on the list. And you know that that's a weak acid and that's a weak
Okay, so the question was about making the list. So just to restate, what I would do for the list, have like acids on the left, bases on the right, list my strong acids, write strong acids, then say weak acids, and just write them down as we learn them. So acetic acid is one of them, HF is one of them. And on the right-hand side, write your strong bases, list the weak bases, right? NH3, really common. F- we talked about, and we'll be adding to that list. Questions? Okay, so finishing up my little sketch here. So I'm adding acetic acid to my beaker. If I had microscopic eyes, what would I see in my solution? Be specific.
Acetic acid.
Acetic acid. Let's write it CH3COOH. That's my favorite way. What else? H2O. What else? Hydronium. H3O+. What else? Acetate. Wonderful. What makes the solution acidic? Which species? Hydronium. Makes the solution acidic, and I remember that because that's the equation I use to calculate the pH. questions? Yes,
So you can calculate pH with hydroxide as well, right?
you can calculate pH with hydroxide, so we're getting a little bit ahead, but our hydroxide is a POH equals negative log of OH minus. So if you have a base reaction, your product is hydroxide. You would first calculate a POH, and then we're going to learn pH plus POH equals 14, and then you can calculate your pH that way. So what does P stand for? pH, negative log of H. POH, negative log of OH. So what does that P mean in our chapter? What does it represent? What would a PX be?
Of your concentration of the ion.
Negative log of X. So a pKa is a negative log of a Ka. pKb, negative log of Kb. pKw, negative log of Kw. So you don't have to memorize a billion equations, just remember Px, negative log of X, and then that will help you. Yes?
In Alex, we had a question that was interconverting like a pKb of this to the negative log version of that.
Yeah, so in Alex, you were introduced to a lot of just the technical equations that we'll be using. We'll be adding to those as we go. So yeah, there's many more equations than just that. If you look at, what is it, page 21 in the study guide, the first page of the acid. So there's so page 22, thank you. The pH equations. So I have a text box on page 22 that gives you all of the equations we're going to use in this chapter. And all of that is really just kind of algebra manipulating. It's like a puzzle, a logic puzzle, to go from one place to another. So throughout the chapter, we'll be using all of those. I just gave a couple introduction equations that students will forget about.
Okay. Yeah, what concerned me was like I could do the first one out of that table on Alex, but the other two was asking like it would give you the negative log Kb and it would ask you to get Kb.
Okay, so a reminder. So just a quick note on the logs on rearranging. So when would I use Px equals? I'll use a real example. So, you guys ready? Okay, so pH equals negative log of hydronium. And when would I use this? What would I be given to use this algebraic form? You're given hydronium and you want to find pH. What if you're given pH and you want to find hydronium? You have to do algebra. So what do you have to do? Divide both sides by negative 1. How do we get rid of the LOG? 10 to the. So Ln is e to the. So then if we want to find hydronium, we do the algebra, which gives us, I don't know if that answered your question. Is that, did it? Cool. So those are our rules of logs, or algebra rules of logs that we need to remember. Yeah. And that'll work for any. So there's a PX, PKW, PKA, PKB. Good. Yeah, it's in the back.
The significant figures for the hydrogen concentration.
Well, so if I have 2 sig figs for my hydronium molarity, I need 2 digits past the decimal for pH. When we actually get to these calculations, we'll go over that. And I posted some on the Facebook group. I posted some helpful tips about that based on students' inquiries. So again, if you haven't joined the Facebook group, it's a good way to have really easy question and answer sessions to help you with the homework. Also, did you guys get the email that I had office hours yesterday, both in person and online? So I had the Zoom office hours. I had one student call in, and it worked. What I did, I have my iPad connected to the Zoom conference. So you could call, if ideally you log in with the app on your phone or with the computer, and you can either talk to me and ask me questions. We can talk back and forth. You can type questions if you prefer that. And I have it set up so it's a screen mirroring my iPad. I can write on my iPad and you can see what I'm writing. So that's a way for office hours. If you can't come to office hours but you have questions, you can access it remotely. So I'll be continuing to do that as well as a way to try and give you guys more chances to get help. Yes?
Is the pH of negative log of hydronium the same as negative log of hydrogen?
Yes. Hydronium and hydrogen, H+, we use them interchangeably. So pH is negative log of H3O+. I can be lazy and say pH equals negative log of H+. The only reason I ever write down H+ instead of H3O+, because I'm being lazy. It's a shortcut. Because H+ is aqueous, aqueous is water, therefore by definition H+ is H3O+. So like when my older lectures, oftentimes I'd have H+ written, then I kind of realized I think it's better, it's more fully correct to use hydronium, and I do my best to do that. But in textbooks and material online, you might see both H+, H3O+, used interchangeably. It's like saying, writing down SEC for second or writing down S for second. Same exact thing. Good question. Any other questions right now? Okay. I wonder why that does that. Okay, auto-ionization of water. This is a very important equation. We kind of only look at it on this one slide. It'll come up a couple of times in the future. But it's a very important equation because it's always going on. We will need to use it in some future Hess's law type problems. Students tend to forget it. I'm a really big fan, I think because I don't memorize things easily. For me, if I can remember the name of something, I'm oftentimes remember to use it. That's why I talk about it. Acid hydrolysis reaction, you're reacting with water. So auto-ionization. So when you hear the word ionize, again, what do we think of? What are we forming if you hear the word ionize? You're going to form ions. Auto, what is that auto-ionization? Auto-self. So reacting with itself. So the auto-ionization of water, water reacts with itself in equilibrium to make hydronium and hydroxide. And again, to be clear, those are real equilibrium arrows. Hydronium and hydroxide. The equilibrium expression for this process is, so if I have an equilibrium reaction, I can write a K expression, correct? What would we write down? Products over reactants. What are all of my coefficients? 1. So what are all of the exponents? 1. So products over reactants, hydronium. What goes downstairs?
Nothing.
Nothing, right? Between 1. Right? And that's because, why? They're liquids. So if you remember our heterogeneous equilibria, solids and liquids are not included. You can have a molarity with water, right? It's pure substance. And this is called Kc, specifically Kw. So that's a Kw reaction, the auto-ionization of water. What does that mean? It's a constant. So Kw is called the ion product constant for water. So this special equilibrium constant is referred to as the ion product constant for water, Kw. And remember, a K is a constant for a given reaction at a given temperature. So if I'm at 25 degrees Celsius, Kw is always 1.0 times 10 to the negative 14. And in our textbook, we always hang out at 25 degrees Celsius. So we're always working at 25 degrees Celsius unless you're told specifically otherwise. So if the temperature was 27 degrees Celsius, would Kw be 1.0 times 10 to the negative 14th? No.
Is there a situation like that where different temperatures given?
Yeah, so I've seen it in some practice tests, and it used to be on the Mastering Chem homework. I don't know if I've seen it on Alex. I think I do. So if I go through the next slide, we'll see why the pH of a neutral solution is 7. So if the temperature is not 25 degrees Celsius, the pH of a neutral solution might be 6.5. And you could back calculate the Kw at that temperature. questions? So this next slide, we're going to go ahead and look at, did I skip a slide? So our auto ionization equilibrium, and now some definitions. So pH, talked about this before, negative log of hydronium. So if you can get the hydronium molarity, you can find the pH. In pure water, Kw, right, is hydronium times hydroxide. If it's pure water, all that means is that the only thing you put into your beaker is this. Again, this is equilibrium. So if I'm putting water into my beaker, what do I actually have there besides just pure water? You've got hydroxide, you've got hydronium, you've got H2O. What is the major species there, though? Water, hydroxide, or hydronium? In pure water? H2O. Why? Remember, this is a really small number. K is really, really small. What do you have mostly? Products or reactants? You have mostly reactants. And we're going to get the actual molarity. So Kw is hydronium times hydroxide, and that's a constant at 25 degrees Celsius. And in pure water, hydronium and hydroxide are equal, right? These are your reactants. Hydronium hydroxide are the products. It's a 1-to-1 mole ratio. So they're the same, so we can solve for hydronium by taking the square root of that, which is 1 times 10 to the negative 7. Again, you're able to use your calculator, so make sure you remember and can find that log button. Therefore, in pure water, pH is negative log of 1.0 times 10 to the negative 7. 2 sig figs in the molarity gives me 2 digits past the decimal point. So, what does that give us? That tells us a neutral solution has a pH of 7. We just talked about that. If my solution is acidic, what do I have more of? Hydronium or hydroxide? Hydronium. So if my solution is acidic, that means my hydronium molarity is larger than the hydroxide molarity. Common sense, right? Acidic, you got more H+. And then the negative log is then going to be less than 7. So if I have an acidic solution, my pH is less than 7. A basic solution, I have more hydroxide than hydronium. And my pH value is then going to be greater than 7. So just a couple notes. My pH scale. What is a pH of 7? Neutral. When am I basic? Greater than 7 or less than 7? Greater. We typically go up to 14. When am I acidic? Less than. How about in a POH? POH, I'm still neutral at 7. And so let's think about the equation. I read this on the board a little while ago. Uh-oh. pH plus P, I'm just going to ignore that, equals 14. So if I have, let's say I'm looking at something easy, 10. So if I have a pH of 10, what is my POH? So my POH then would be 4 to 0. So this is my basic region. If I have a pH of 14, I've got a POH of 0, right? That is still basic. So a low pH is basic. Sorry, a low POH is basic. And what would we say about a higher POH? So if I have a pH of 2, what is the POH? What equation do we have to do? This one, right? If I have a pH of 2, what's my POH? 12. So a POH of 12 is acidic. So based on the equation, pH plus POH equals 14. High pH, I know it's basic. A low POH is also basic. So they're essentially inversely related. Yes?
Can you explain one more time? So, why did you take the square root of 1.0 times 10 to the power negative 14?
So the question was, why did I take the square root of 1 times 10 to the negative 14? Because my H plus and OH minus are the same, 1-to-1 mole ratio, so we could say they're both equal to x. X squared, we can take the square root. And we'll be doing that again in the next practice exercise. And I don't tell you it's exactly what I just did, I just ask you to do it, but it is exactly what we just did. So we'll see it again. Any other questions on this? So what I would like is to write down this pH-POH scale. I think it's actually on the first page of your study guide, but to understand how this pH plus POH equation works. And to realize high pH is basic, a low POH is also basic. Yes?
So pH plus 10 is your pOH.
pH plus POH is 14.00. So you'll plug in a pH is 2, so then I know my POH is 12 because 2 plus X equals 14.
And 14 is
14 is it comes from our KW of 1 times 10 to the negative 14. So this equation, pH plus POH equals 14, you need to memorize it and know that you can use it. So that's like a given.
oh 14 is a
14.00 is a constant that's related to that KW. Questions? Okay, so practice exercise 4. We calculate the concentration of hydroxide in a solution, and I give you hydronium. So we'll be using a couple different equations. I'll write them on the board. And I would encourage you, have that chapter 16, that first page, those pH tables out when you're working on these practice exercises. The equations I think of. And remember, H plus is the same as H3O plus. Okay, so I wrote those equations in green. Those are from the front of your study guide. These are all of the equations that you might need to use. Are you going to use all of them? No. Is there more than one way to do any of these problems? Yeah, oftentimes there is. So, go ahead, work through this, and we'll go over it together in a minute.